Magnetic fields due to electrical current. Ørsted discovered the magnetic field around a current-carrying wire back in 1820. He had a wire carrying no current passing along the top of a compass needle. When a current flowed, the compass moved through 90 degrees to be perpendicular to the current. If this is a wire carrying a current in the direction shown by the arrow, the magnetic field around the wire is something like this, concentric circles. You'll see that the circles are getting more widely spaced as we go further out, showing that the field gets weaker as we go away from the wire. To give the direction of the magnetic field, we can use the right-hand grip method. If you go to grip the wire and point your right thumb in the direction of current flow, your fingers will curl in the direction of the magnetic field. To avoid drawing complicated three-dimensional diagrams, this notation is often used to show a current moving towards us, as if a wire is coming out of the screen towards you. It could represent the point on the end of an arrow coming towards you. We find the magnetic field then is like this, which you can verify by using the right-hand grip method. Point your thumb towards you and your fingers will curl in the direction of the magnetic field arrows. The current moving away from us can be represented like this. This could be the flights of an arrow moving away from you. And now the magnetic field will be in the opposite direction. If we have a loop of wire carrying a current like this, then the wire at this point is carrying a current towards us, and so it will have a magnetic field like this. Here the current is away from us with this magnetic field. If we put in the rest of the field lines, we get something like this. Here we have several current-carrying coils together, making up what is called a solenoid, with the current flowing up here, round the back, up here, and so on. This arrangement produces a magnetic field something like this, with the magnetic field lines coming out of here, making this the North Pole, coming round and into here, making this the South Pole. You'll recognise this as the field produced by a bar magnet. The strength of the magnetic field, or the magnetic flux density of a solenoid, is affected by the number of coils, the current passing through the coils, and the material inside the coil. You don't need to be aware of the formulae used to calculate such quantities.